You write x equals 42 in Java every day. Have you ever wondered what's really happening inside your computer? Today, we are going to crack open the black box and see the ones and zeros that make your variables come alive. By the end of this video, you will understand exactly how this simple line of code becomes a pattern of electrical signals bouncing through billions of transistors. Let's start with the most fundamental truth about computers. Each LED represents one bit of computer memory. We need to control it turns on and off. So I added a switch here to control the power flow. When I press the button down, the LED lights up, and when I release the button, it goes dark. Every piece of data in your computer starts here, with something that's either on or off. These LEDs represents the most basic building blocks of digital information. On is 1, off is 0. Everything your computer does, from storing your variables to running complex algorithms, all comes to patterns of ones and zeros. Look at this pattern of LEDs. It's on, off, on, off, on, off, on, off. So if we translate this pattern of LEDs into numbers, it will be 1 0 1 0 1 0 1 0. So what does this binary patterns actually mean? Actually, from left to right, the first light is represent 128, and the second light is represent 64, and the third light is represent 32, and the fourth light is represent 16, and the fifth light represent 8. The sixth light represent 4. The seventh light represent 2, and the last light is represent 1. So if we translate this binary pattern into the decimal number we're familiar with, actually we need to do is multiply each number that the LED represents with the binary pattern and plus all the numbers. So we can ignore the light is off because every number multiplied with 0 is 0. So we just need to plus 128 with 32 with 39, and the fifth light 8, and the seventh light, which is 2. Then we get the number. Which is 170. That's it. But you might be curious about why just ones and zeros. Why not just use 1, 2, 3, 4, 5 like we normally count? Inside your CPU, there are billions of tiny switches called transistors. Each transistor has three parts: input, output, and the control. The control decides whether the electricity flows through or not. And each transistor only can be one of the two states: conducting electricity or not conducting electricity. When there is a control signal present, and the electricity flows through, then we call this state is 1 or true. If there's no control signal, and no electricity flows, then we call this state 0 or false. If you grew up 8 transistors together, I represent the transistors with T. Then you got what we call a byte, which is the fundamental unit of computer memory. These 8 LEDs represent 8 bytes. They have their own state. Every variable you declare in Java ultimately will become a pattern like this and stored in your computer memory. Humans use 10 base because we have 10 fingers, but computer only have 2 states, on and off, so they use 2 base or binary. In binary, you can only use 0 and 1. When you run out of digits, you add a new position, just like in decimal. Now let's try convert 42 to binary. Each of the position of these LEDs represent a power of 2. From right to left is 0, 1, 2, 3, 4, 5. 6, 7, and the value is 128, 64, 32, 16, 8, 4, 2, 1. I will show you a method that actually matches how computers think about this. First, we take the number 42, go through all the value from left to right. Actually, from the greatest to the minimum. Let's see. First, we compare 42 with 128. It's less than 128, so this bit is 0. And then we compare 42 to 64. It's also less than 64, so it's also 0. Then we got 42 is greater than 32, so this bit is 1. And we have 42 minus 32 equals 10, so we have 10 left. Then we take 10 to continue. 10 is less than 16, so this bit is 0. But 10 is greater than 8, so this bit is 1. Then we left is 10 minus 8, so it's 2. We got 2 left. 2 is less than 4, so this bit is 0. But 2 is equals to 2, so this bit is 1. And 2 minus 2 is equals 0, so we got 0 left. And 0 is less than 1, so this bit is 0. Then finally, we got the binary pattern 0, 0, 1, 0, 1, 0, 1, 0. So we can see the 42 in decimal equals this pattern in binary. Let's verify the result on our LED display. The result we got for 42 is in binary is 0, 0, 1, 0, 1, 0, 1, 0. So we put on the LED display is off, off, on, off, on, off, on, and off. So let's calculate the number from left to right is 128 plus 64 multiply 0 plus 32 multiply 0 multiply 1 plus 16 multiply 0 plus 8 multiply 1 plus 4 multiply 0 plus 2 multiply 1 plus because every number multiplied with 0 is 0, so the only result is 32 plus 8 plus 2 equals 32. So the result is correct. Now pause the video. Try to convert your age to binary by using the same method, using the powers of 2, and write down your zeros and ones. For example, if your age is 25, it's obviously 25 is less than 32 and greater than 16. So the first one will be in the 16, or we can say from left to right is the fourth. And then we write 3, 0, and 1. Then we got 9 left. So we compare with the next number, which is 8. 9 is greater than 8. So 9 multiply 8 is 1. So then this bit is also 1. Then we got 1 left. The 1 is less than 4 and 2. So we got 2, 0 in next 2 bits. Then 1 is equal to the last bit represent number 1. So 1 minus 1 equals 0. And we got this bit is 1. Then we got 0 left. So finally we got the binary pattern is 0, 0, 0, 1, 1, 0, 0, 1 is the decimal number 25 in binary description. When you write down this line of Java code, the computer doesn't see the number 42. It only sees the binary pattern we just created. The pattern of zeros and ones gets stored in 32 bits of computer memory. This is because Java's int type is exactly 32 bits. Why 32 bits? How many different values can store in 32 bits? As we already know, 10 powers of 2 equals 1024, and 32 powers of 2 equals 3 of 10 powers of 2 multiply and then multiply 2 powers of 2. It's like roughly 4 billion from negative 2 billion to positive 2 billion. It's quite a lot of values. It could cover mostly logical scenarios. When you declare int x equals 42, Java will find out 32 bits available memory to store the binary pattern there. So that will be like this. Will be 4-bit. Each bit with 8 bits. For example, the address 1000 point to the first bit. Each memory address can hold exactly 1 bit. Which is 8 bits. So our 32-bit integer actually spans 4 memory locations. For each bit can have its own address. The computer will treat these 4 bits as a single unit, which is your integer variable. Now let's both think a question. If the value of x is not 42, it's like 1024. How would this binary pattern will be? You can pause the video and think in your head. Actually, it's 1 with 10 zeros follow. So we can see if a number exceeds the capacity of 1 bit, it will expand to another bit. Every variable you create in Java, integers, characters, objects, they all start here, with a pattern of ones and zeros flowing through transistors. In our next video, where your variables actually live, we'll explore the memory hierarchy and discover why understanding computer architecture makes you a better Java programmer. Subscribe, and I will see you in the next one.